morning, students. Today we will start the second part of the rotational spectroscopy. So the next question in this topic will be like this: what is the selection rule for rotational transition? Derive an expression for energy changes and frequency changes due to the transition in the rotational energy level. Means there are two parts of this question. In the first part, we have to discuss the selection rule which is applied in case of rotational transition or rotational spectroscopy, and in the second part of the question, we have to derive an expression for the change in energy when a particular transition takes place among the rotational energy levels. So, for answering this question, we first draw a number of rotational energy levels. Rotational energy levels are denoted by J. So, J is equal to 0 means first rotational energy level, J is equal to 1, similarly J is equal to 2, J is equal to 3 and J is equal to 4. Now, the selection rule for rotational transition is this one: delta J is equal to plus minus 1. That is, the transition can take place among the adjacent rotational energy levels. That is, from the lower rotational energy level to the upper energy level, which is just adjacent to each other. Either it can go upwards or it can go downwards. So here we have shown some transition. For example, this is the first transition, J is equal to 0 to J is equal to 1. This will be delta J is equal to plus 1. Similarly, this transition is also valid. Delta J is equal to 1 to J is equal to 1 to J is equal to 0 means delta J is equal to minus 1. Similarly, here also this transition is J is equal to 1 to J is equal to 2, that is delta J is equal to plus 1, and again here J is equal to 2 to J is equal to 1, that is J is equal to delta J is equal to minus 1. Similarly, all these transitions are in the same way. Now we have shown here there are other transitions also, that is J is equal to 0 to J is equal to 2, J is equal to 0 to J is equal to 3, J is equal to 0 to J is equal to 4. According to the selection rule, these transitions are not valid and are called as forbidden transition. So we have put the sign cross here, and these are the transitions which are according to the selection rule. Hence, these are called as allowed transitions. So now delta J is equal to plus minus 1 means delta J is equal to final value minus initial value. Now let us consider, now we have to derive the expression for the energy change when a transition takes place in the rotational energy level according to the selection rule. So for this we have drawn two energy levels. One is upper energy level denoted by J prime, and the lower energy level J double prime, and here a transition has been shown from J prime, which is upper rotational energy level, to J double prime to the lower rotational energy level. The corresponding energy of J prime, which is upper energy level, is E prime R. R is written for the notation of rotational energy level. Similarly, for energy of J double prime, that is energy of lower rotational energy level, is given by E double prime R. Now, if you want to know what is the energy change, what will be the energy change when this transition takes place, so that will be equal to delta E is equal to E prime minus E double prime. That is the energy of this energy level minus the energy of this energy level. Now we have seen that in the previous lecture that the energy of rotational energy level can be given by h square by 8 pi square I J prime into J prime plus 1, and for E double prime h square by 8 pi square I J double prime into J double prime plus 1. Now we simplify this expression, then the common is taken out, and inside the bracket we have only j prime plus 1 minus j double prime plus 1. Now if we want to write this expression in terms of rotational constant, which is b, and b is equal to h by 8 pi square IC. So this expression changes into BHC, and remaining portion is same. And delta is the change in energy of the rotational transition, and B is the rotational constant. So we have discussed in our previous lecture that the energies which are expressed in rotational transition, or in case of any spectroscopy, is more suitable in terms of the wave number. So when we want to express the energy in terms of wave number, then we have to divide the energy change by Hc. So for this we have to divide left hand side and right hand side, both sides, the expression with Hc divided by Hc. So when this expression is divided by Hc, this is also divided by Hc, and now this is equal to nu bar. We have shown in my previous lecture that this comes out to be delta nu bar, which is wave number. And now this becomes h by 8 pi square IC, j prime into j prime plus 1 minus j double prime plus 1, and here the unit also changes. In this case we have seen that the unit is joule, but when it is expressed in terms of wave number, the unit becomes centimeter inverse. And finally we give the expression by this wave nu bar is equal to b j prime into j prime plus 1 minus j double prime plus 1 per centimeter. Now another important question in this case is that show that the spacing in case of rotational spectra is 2b. Rotational spectra is 2b. This is spectra. Spectra means the spectrum obtained in case of rotational spectroscopy, not the energy levels. This is a very important question. Spacing in case of rotational spectra is 2b, whereas where b is the rotational constant, and the spacing between the two adjacent lines means, it's another way we can say that the spacing between the two adjacent lines in the spectrum is 2b. So for answering this question, we have drawn again some energy levels. Suppose this is this energy level is J, then this energy level is just adjacent and above J, so it will be written as J plus 1, and this energy level is adjacent to J but just below J, so it will be written as J minus 1. Now suppose we have a transition from J plus 1 to J, then this will be the transition, and for this transition we have notation like this: J plus 1 to J, J plus 1 to J nu bar. So now nu bar is equal to B J prime plus 1 minus J double prime J plus 2. The same formula has been used here, and the only change is that the upper energy level is J plus 1 and the lower energy level is J. So in this formula here, for J prime we will use J plus 1, and for J double prime we will use J. So it becomes J plus 1 and J plus 1 minus J into J plus 1, and when this is simplified, it becomes J plus 1 into J plus 2 minus J into J plus 1. J plus 1 is taken common, then it becomes j plus 1 minus j, it cancels out and then becomes 2bj plus 1. Now, in this case, we have taken a transition j plus 1 to j plus 1 to j. Now, if we want to take another transition which is just at the side of the previous one, that is this one, then we have to show the transition j to j minus 1, and that is we have shown here from j to j minus 1, j to j minus 1. Here transition is j plus 1 to j, and another transition is here j to j minus 1, and these two transitions are adjacent to each other, just side by side to each other. And now we calculate what will be the expression in this case. So again the same formula is used and the same type of notation is used, j to j minus 1, j to j minus 1, this is the notation. And for here the upper energy level is j, so it becomes j into j plus 1, and the lower energy level is j minus 1, so j minus 1 into j minus 1 plus 1. And now when simplified, it becomes 2bj, where j is 1, 2, 3 but not equal to 0. Because it becomes 0, then if this becomes 0, then j minus will be negative. So there is no negative energy levels. The minimum energy level is j is equal to 0. So therefore this cannot be 0. That is, the lower transition cannot arise from j is equal to 0. Now, if we want to represent these two transitions, this one in from figure 1 and from figure 2 at a same place, then this type of figure we can draw. Again, the same figure is here. This is rotational energy level j. This is just upper rotational energy level and j plus 1, and from the lower energy level just below j is j minus 1. This one is the transition. This one is the transition from j plus 1 to j, and this one is the transition from j to j minus 1. For this transition, the line which is obtained in the spectrum is this one, and for this type of transition, the line which is obtained in the spectrum is this one. And when we take the difference between these two energies between these two lines, we will have the value of the spacing, and this comes out to be 2b. So the value of this transition is just we have calculated 2bj plus 1. It is 2bj plus 1, and the value of this transition is 2bj. This is 2bj. Now we take the difference between these two. So this is the expression for taking the difference. Delta j is equal to delta nu bar is equal to nu bar j plus 1 to j, means this one j plus 1 to j, and another is from j to j minus 1, and if value is taken here, its value is 2bj plus 1 and its value is 2bj, and when we take the difference and solve the equation, 2b comes out as common, j plus 1 minus j, so it becomes 1 and the spacing becomes 2b. So this is the answer of the question, that the spacing between the two adjacent lines in the spectrum of rotational spectroscopy is 2b, where b is the rotational constant. Now, another important question may be like this: show that in case of rotational spectroscopy, the rotational energy levels are not equidistant, but the lines obtained in the spectra are equidistant. Just we have answered this. There are two parts of this question. In the first part, we have to answer, but the second part of the question has been already answered just in the previous slides. So we have to just see that how the rotational how the rotational energy levels are not equidistant, because we have just shown that the obtained like this, and different lines in the spectrum are like this, and the spacing between two adjacent lines is just 2b. Here it is also 2b, here it is also 2b, here also 2b, here it is also 2b. So this has been already been shown. Now we have to show that the lines energy levels in the rotational energy levels are not equidistant. So again we have some energy levels. This is J is equal to 0, lowest energy level, J is equal to 1, first energy level, J is equal to 2, second energy level, J is equal to 3, third, fourth, and so on. And the energies of these energy levels can be given by from the expression of either in terms of energy or in terms of wave number. So in terms of energy, it is 2BHC J into J plus 1 joules, or in terms of wave number, it is BJ J plus 1, where B is the rotational constant. So in both the terms, we can express the energy levels of a rotational energy level. Here, in this expression, if we put J is equal to 0, so whole thing becomes equal to 0 and it comes 0. So energy is 0. That is energy of this energy level, that is J is equal to 0, is 0. If we take in terms of wave number, then again we have to put J is equal to 0. So when we put J is equal to 0, it again becomes 0. So nu bar will be also 0 for first energy level, that is J is equal to 0. For second energy level, which is J is equal to 1, we have to put 1 in this case, also 1 in this case, and the expression becomes like this: E is equal to 2 BHC. If we put 1, then 1 plus 1, 2, and 2 BHC, and here it becomes 2b, because here we put 1, so 1 plus 1 into 1, so 1, 2 into b, so 2b. Now if we take the difference between these two energy levels, then 2b minus 0, so it is 2b. Again, these are the values which are obtained from this formula. So nu bar is equal to 6b, E is equal to 6BHC, nu bar is equal to 12b, 20b, 30b. Here is also in terms of energy. And if we take the difference, here the difference becomes 12b minus 6b, 6b. Here the difference becomes 6b minus 2b, it is 4b. Here it is 20b minus 12b, 8b. Here it is 30b minus 20, then it is 10b. So difference between the two energy levels is not constant. It is continuously increases as we are increasing the value of rotational quantum number J. So first difference is 2b, second difference is 4b, third difference is 6b, then it is 8b, then 10b. That is, the spacing between the rotational energy levels are not constant. So this is the answer of first part of this question, and for second part we have just answered in the previous slide. So nothing I have to discuss, only from figure we can see that is again we are getting the difference same between this is the spectrum, and in the spectrum the difference between the two adjacent line is 2b, that is constant. This is the characteristic of rotational spectroscopy. Now intensity means how much intense is the line. Line is how much intense. Line appears in the spectrum, then how bright it is. The brightness is called as the intensity of the spectral lines. So here again we have drawn some rotational energy levels. J is equal to 0, J is equal to 1, J is equal to 2, J is equal to 3, and according to the selection rule we have shown the different allowed transitions. Selection rule is delta J is equal to plus minus 1, and intensity actually depends upon the population of energy level. Population of energy level. These are the energy levels, and the population of energy levels mean how many particles are present in these energy levels. The number of particles present in these energy levels is called as the population of energy level. If a particular energy level is highly populated, then there is a chance of transition of those particles from lower energy level to the upper energy levels, and the intensity will be more. But if the population of particular energy level is low, that is number of particles in a particular energy level is low, then naturally there will be less transition, and the resulting spectrum, the resulting line in the spectrum will have a low intensity. But this intensity, which is directly proportional to the population of the energy level, is governed by these two factors. One is Boltzmann distribution, and another is degeneracy of the energy level. The Boltzmann distribution is given by this formula, where the terms has been defined like this: Nj is equal to population in the jth energy level, N0 is the population of energy just below the jth energy level, Nj is delta Nj is equal to energy difference in these levels, and Kb is the Boltzmann constant, T is the absolute temperature, and Ge and G0 are the degeneracy of the energy levels. Degeneracy of rotational energy level is given by 2J plus 1. This has been established, where J is the rotational energy level, and J is equal to values of J are J is equal to 0, J is equal to 0, 1, 2, 3, etc. So population will be proportional to this degeneracy into energy, degeneracy into this energy term here. Now there is another question in this part, that what is the condition when a maximum intensity is obtained. So we will have to derive this formula: J max is equal to under root K T by 2 BSc minus half. For deriving this formula, we have to start from this point. This population is denoted by P, and P is proportional to 2J plus 1 e to the power minus delta E by Kb. K is the Boltzmann constant, B is written for the Boltzmann constant. We can write only K also here. So if we differentiate this P with respect to J, and for first differentiation with respect to J, we equate the equation with 0, then we will get a condition when we get the condition for the maximum intensity. So here we have done the same thing. Here this expression has been differentiated with respect to J, and finally this d by dj of population is equated to 0, and when it is simplified, it becomes delta J max is equal to under root Kt by 2 BSc minus half. On this expression we will have numericals also. So we have to know the values of absolute temperature, Boltzmann constant, rotational constant, h is the Planck constant, c is the velocity of light. We will easily calculate the value of J max. Here from the same expression, this T is the absolute temperature at which transition is occurring, and this is also called as temperature of flame. J max is the maximum intensity of the corresponding rotational spectra. So today I am concluding this part here. From next day, from here we will start the another part. Thank you.